Okay, we'll go ahead and get started. Welcome everyone to today's GPG webinar on a new alternative water treatment that we've just evaluated on continuous monitoring and partial water softening. And before we get started, I want to go over just a few webinar logistics. Today's webinar is based on our full report by the National Renewable Energy Laboratory, and you can find the full report as well as the one-page infographic and four-page findings on the GSA website at gsa.gov/GPG. Today's webinar is being recorded, and you can find a recording. We'll be posting recording of the webinar as well as presentation slides on the GSA website, as well as sending them out after. And the webinar is available for continuing education credits, one continuing education credit from the American Institute of Architects. And to receive credit, you need to complete a post-webinar survey that we'll be emailing to you. And if you don't receive a copy of the survey, please reach out to Michael Hobson. You all are in listen-only mode, and so, but we ask you to use the Q&A button to ask questions, and you don't need to wait until the end of the session to ask questions. In fact, it's helpful to us if you ask them throughout. So please, use that Q&A button to put your questions in there. And then with that, I'd like to turn it over to Jay Fine, who is the project manager for the evaluation and will be facilitating today's webinar. Jay.
Thanks, Andrea. I'd like to add my welcome to everybody. Glad you could join us today. As Andrea said, I am a project manager, and I did actually manage this project for GSA. If there are questions that we don't get answered today, I'm probably the right person. You can feel free to send me an email or give me a call. Next slide, please. All right, here's what we're going to do today. So first up, we're going to have Kevin Powell, who's the director for GSA Center for Emerging Building Technologies. Kevin's going to do just kind of a quick intro of the technology and get us kind of kicked off and get your appetite wet for what's going to come up after that. We'll be followed by Greg Tomberlin, who's with the National Renewable Energy Laboratory. Greg was the principal investigator for this project. He's going to tell you what we did and what the outcome was. And then after that, we always like to do kind of a boots on the ground, give you some practical feedback for what it was like to actually have these technologies installed in our buildings. So we're fortunate to have with us Jacob Lewis, who's the GSA Deputy Property Manager at the facility where this was evaluated. He's going to give you that feedback. And then it's going to come back to me. I'm going to tell you about some other alternative water treatment technologies that we've evaluated. And then we're going to jump into Q&A after that. Okay, with that, I'd like to turn it over to Kevin.
Well, thank you, Jay, and thank you all for having joined us this morning. As I think many of you know, but some of you may not, the reason we have a Proving Ground program here at GSA is to address the fact that there's a lot of innovation out there. And there's a lot of investment actually in bringing that innovation to the marketplace essentially. But once it gets there, there's really a lack of objective performance data that says, hey, this new technology actually delivers, or this new technology delivers in this particular kind of application, or honestly, this new technology isn't really ready for prime time. And that's really what our program is set up to do, and that's what these studies are all about. They're really designed to help GSA with those kinds of investment decisions, to make prudent ones based on real world performance. Next slide. So I think if you look at that bottom number, you can certainly understand just the financial driver of why we would be very concerned about saving water, and particularly in the largest single use of water in a building, which is the cooling tower. Buildings that have cooling towers, that is the largest single use. It's actually something that is easy for us to control and to impact. So again, that's the notion of why we've been looking at all these different alternative water treatment technologies. And for those of you who've been tracking our program and these outbriefs, there's been a number of these AWT solutions. We're actually going to come up with some comprehensive guidance in the next year. Next slide. So this particular technology, just to cue it up for, again, why did we select it, and why did we select it, I guess is the key question. And the answer is that what we've found with other AWT technologies that we've evaluated is that a number of them really do work. They can be made to work, certainly, but the challenge with them is that to make them work, they require a different approach to O&M practices. So you cannot continue to do the same exact O&M practices as you potentially have contracted for when you apply this new AWT technology. So it works, but it works with a different set of operating parameters, and that's actually a challenge to adoption. This particular technology allows you to keep your existing O&M practices, no change, and actually it improves, essentially the effectiveness and ease of those O&M practices. So it's essentially something that's helping you do your job better and saving water. So with that, I'm going to turn this over.
Hi, good morning. My name is Greg Tomberlin. I'm an engineer with the National Renewable Energy Laboratory in Golden, Colorado. And as Jay mentioned, we were the principal investigators on this project. We were the ones who went out and installed instrumentation, collected data, and then ran economics to try to figure out what the savings and the economic payback were on the project. Next slide. I think Kevin touched on some of this. I mean, traditional cooling tower water treatment programs use scale and corrosion inhibitors and biocides for biological growth. And they control a lot of the chemistry with these chemicals and then also with blowdown. The problem is the blowdown is where all this water goes, and typically 25 to 50% of the makeup water is discharged as blowdown to the sewer just to minimize the collection of minerals and scale buildup. And on the right, we just have a couple of metrics. The evaporation is where the rest of the water goes. That's about 1,000 BTUs for every pound of water that's evaporated, and that's close to 2 gallons per every ton hour of cooling that takes place. Again, we can't do anything about the evaporation, but we're targeting reducing the blowdown in the system. Next slide. This is basic, and I apologize to people that are very familiar with cooling towers. I won't take a lot of time on this, but this is a cooling tower graphic that basically shows the water goes to a heat exchanger typically, which is the condenser on a chiller. The warm water goes back to the cooling tower where it's sprayed over a fill and evaporation takes place, and that's how the cooling takes place. When the water evaporates, then all of these minerals are concentrated into the cooling tower basin water. And to get rid of those minerals, you have to blow them down and basically drain them to sewer, and then you make up with clean water. There's also another water loss that's small. It's called drift. As the cooling tower fans blow through the system, water droplets leave the system. So when we did our calculations and the water balance on the system, we calculated the drift losses also with a formula. Next slide, please. So cycles of concentration is something I think most people are familiar with. If you look at the first bullet, the cycles of concentration is equal to the amount of water that's being made up to the system divided by how much you blow down. So if you decrease the blowdown, you're increasing your cycles of concentration. So the higher cycles, the better. Typically on these GSA sites, the cycles of concentration run between about 2.5 to 7, probably closer to the 2.5 range. And if you look at the savings in this graph on the right, you can see, I don't know, could anybody see my cursor too? Or probably not. Yeah, okay. So if you look at the steep part of the curve, you're seeing a whole lot of blowdown in that 3 to 10 cycle range. And that's where most of these places operate at. So to get savings, we're trying to increase the cycles of concentration. Once you get up to 10, potentially 15 cycles, the savings level off. So the target's typically somewhere between 10 and 15 cycles if you can get there. And just as a reference, that last bullet shows that if you're at a cycles of concentration of 3, which was about where we were when we started this project, you have about 33% of the cooling water makeup just being wasted as blowdown. Next slide. So the primary objective of our testing, we in essence went out to the job site and installed a lot of instrumentation. You can see on the right some of the typical points, that we measure. We measured the chiller condenser water supply and return temperatures. We measured the status of condenser water pumps and chillers, so we knew which equipment was operating. So when we took our data, we knew that data was applicable. We looked at chilled water supply and return temperatures. So when we did our calculations on loads, we had something to compare to. We also looked at ambient temperature and humidity. We had sensors on site that looked at both of those, so we could compare loads with ambient conditions. And then the big ones were the last two. We measured the flow rates of the cooling tower makeup and the cooling tower blowdown. So we put all of this system on, we put in data loggers and cell modems so we could collect all the data, and then we ran a baseline, in essence, to see what the water usage was at the site under normal conditions. And then once the technology was installed, we collected data for a longer period of time to see what the changes were and what the water savings were. And since the loads are different between the baseline and the testing periods, we had to compare apples and apples. So we looked at it based on load, and we calculated load primarily by the quantity of evaporation. So the metric that we ended up with was basically 1,000 gallons of water used per ton of evaporation, and that's the metric we use for this project and for comparing to other technologies as well. Next slide. So this is a picture of the site. This is the Lloyd D. George Federal Building in Las Vegas. It was chosen for several reasons. One reason is it's got a very long cooling season. And just to give you a kind of a size reference, they have their one 450-ton cooling tower and two 300-ton cooling towers. Load-wise, I think we measured they ran about 1.6 million ton hours per year of cooling. In fairness to the vendor, our initial target was around 3 million. We didn't find a site that had that large of a load, so we used this, which was approximately half the load. The technology still proved advantageous. I think, as you know, most of these technologies, or all technologies, really economically are a function of economy of scale. So a larger system fares better, but we use this at 1.6 million ton hours. Anyway, and if you can look at the picture on the left, this is a picture of the technology installed at the site. As you can see, it's a very small skid, sits in the corner of the room. It's got a little brine tank to the left of it, but still it doesn't take up a lot of space. So that skid basically dropped in, tied into the water piping, and then there's also drain piping. So when it comes to installation, it makes sense to put it as somewhere close to the cooling water supply piping and to a drain, because a lot of the cost associated with it, installation wise, is the piping cost. Next slide. This is, okay, it's continuous monitoring and partial water softening. This is basically just a look at partial water softening, and it's normal water softening technology. There's nothing really new about the water softening part of it, other than it's more precise. It does partial water softening. It's not blunt force water softening. It basically monitors 30 points of water chemistry, and then it softens the water as required. It works alongside the chemical water treatment, as Kevin mentioned. It just sits in the corner. You could valve it in, valve it out. It doesn't really affect the other operations on a day-to-day basis. And again, it works like normal water softeners. It has a resin and ion exchange, and then it uses salt in the brine tank to regenerate. And some people might ask, why not just use a full water softener? That can get you into different levels of corrosivity. And what this does is monitors the water. In essence, it uses Langelier and Reisner indices basically to see if you're in a corrosive environment or a scaling environment, and it adjusts appropriately. And if for some reason you get out of line in either of those cases, it actually has alarms as part of the continuous monitoring system that will tell you that you're in trouble. Next slide. The system actually also comes with a side stream filtration system that filters out some of the debris and organics and some of the bacterial components and contaminants. Doing that can actually help reduce corrosion. It also can reduce biofilm on heat transfer surfaces. So if you can develop film like on your condenser tubes and that kind of thing, side stream filtration will actually help with that, which can result in heat transfer energy gains. As part of this project, we didn't measure energy differentials or energy usage, but that's a potential for this project. And while filtration is advantageous and this is helpful to have this as part of it, it's not sized on this system as robust as a side stream filtration system you might get if you go out and contract and bid for one separately. Next slide, please. The real-time monitoring component is the other side of this, and I think that's a real advantage to this system. It does a lot of monitoring of system conditions, and it's got alarms set for targeted maintenance. If you get into a scaling upset condition, if you lose, corrosion inhibitor or scale inhibitor and you get out of line, you can set these alarms. It actually measures system performance with 30 different data points. So it's a great addition to a BAS system, and it can keep you out of a lot of trouble and troubleshoot different areas that could be problematic for the system. And it does tie in also to the BAS. It can use BACnet or Modbus, and I think Jacob Lewis is going to talk a little bit more to this later in the presentation. Next slide. This is just a graphic of water softening showing how this works. It's a typical water softener. It's filled with resin. Hard water goes in and filters through the resin and does ion exchange. And then again, the brine tank is there also. Basically just uses salt, and the salt brine is used to clean the minerals off of the resin and regenerate the resin as part of the water softener. I think most people are familiar with this, so we'll go to the next slide. So the results, again, we started here when we did our baseline testing. We had cycles of concentration at 2.8. When we added the system, we actually changed the conductivity setting on the blowdown controller for the cooling tower. We took it to cycles of 4.2. So this reduced blowdown, and we ended up with this water savings of about 15%. That's the makeup water savings, and that translates also to a 52% reduction in the blowdown. And one thing we do when we change the cycles of concentration, you want to make sure that nothing else is going wrong. So we monitor the system. We look at water reports and water quality data before and after. And actually GSA has a table of water quality standards that we have to stay within that range. So nothing really changed as far as the water quality. We didn't get out of line in any direction. We didn't see any additional scaling or any other problems associated with the system. We looked at cooling tower cleaning and the scale that shows up on cooling tower fill and that kind of thing, and the system looked great. So the bottom line is water savings on this project was at about 15%. Next slide. Wanted to look too at some of the other peripheral issues associated with it. The installation, is it easy to install? Does it take a lot of time or manpower, and what are the costs associated with doing that? The installation took approximately 2 days. That was our target. As you can see, it's a small skid. Sits in the corner. It's got the brine tank. It weighs a total of 1,275 pounds when it's dry when you bring it in, so it's not a heavy piece of equipment. 30 by 30 inch footprint. It's 91 inches tall, but I'm told by the vendor that their newer model is even shorter than that. And again, where it's located is probably key. It doesn't take up a lot of room wherever it's located, but if you can get it close to the water supply so you can tap into that, and then you need a drain also. Because when this system is installed, the blowdown no longer happens at the cooling tower. The blowdown actually happens at this system as it's monitoring everything that it monitors and controlling blowdown. The blowdown happens here, so a drain would be required. So again, it was a simple installation, brought in a skid, dropped it in, and piped it up. Not a whole lot of issues there. Next slide, please. O&M too, we wanted to make sure, we don't have the right graphic there, sorry, but again, this works alongside the normal chemical treatment. So the operations and maintenance side of things is not a lot. There's salt associated with the brine tank, so that has to be loaded into the brine tank system. But we didn't see any other additional operations and maintenance costs, again, associated with like cooling tower cleaning. If we ended up with a scale, like an increased scaling system or a harder scale, you know, you could use more man hours to clean the system up, but we didn't see any of that. So the operations and maintenance really didn't go up, other than costs for salt, some labor for putting the salt into the brine tank. And there's some small calibration that's required too, and we'll go over those costs here in a minute. Next slide, please. So our target here was to have less than a 3-year payback at the 3 million ton target load. And again, we didn't have a 3 million ton system here. We were only at 1.6 million. So the cost, in essence, for this system totaled out at $38,371. I don't show a breakdown here, but roughly speaking, the GSA cost for the equipment itself was about $26,500. There was some on-site training at about $2,300. The shipping costs were at $2,000. And then the actual installation cost with all the piping, bringing the system in and setting it up, was at $6,700. So we totaled out at $38,371. The annual maintenance costs were $783, and that's about $500 worth of salt. And then there's just a few $100s in there extra also for annual calibration of some instrumentation. We looked at the annual energy increase also, because the system does actually have a plug load and uses some electricity. We tallied that it had about 7,700 kilowatt hours a year, which is not a lot on that site. The cost of electricity was 11 cents, so the power requirements or the energy usage were at $850 on top of that. And the big one was the water savings. We looked at water savings at the rate of the average GSA rate of $16.76 per 1,000 gallons. That got us to about almost $15,000 of water savings on the project, which results in a payback of 2.6 years. We also use a metric of savings to investment ratio, which in essence is 15 years. We look at 15 years of savings and divide it by the capital cost and look at what that ratio is too. But our target again was less than a 3-year payback. We met that at 2.6, and we also met the savings to investment ratio target. We can go to the next slide, I think. Okay, I will go ahead and hand this off then to Jacob Lewis. He's the Deputy Property Manager at the site, and he's going to give you some more perspective and insight of the actual on-site issues.
Hi, thank you. Hi, my name's Jacob Lewis. I'm the Deputy Property Manager for the Nevada Field Office. Throughout the duration of this project, I was the main point of contact for the facility. I was also the project manager for the actual installation. Next slide. So Greg had mentioned that the whole installation took approximately 2 days to get this all installed, and that included installing the meters for the evaluation. We were in a unique situation at our building because we had a pre-existing piece of equipment that quite frankly didn't work, that our mechanics ended up shutting off and was just sitting there collecting dust. So for us, it was as simple as yanking out that old piece of equipment and installing the Aqualogic. That consisted of connecting to the supply and return condensate lines. We did have to run fresh water. We did have to tap into the fresh water line and run copper from the adjacent room. And then, like Greg mentioned, we had installed the piping for the drain. Next slide. All right, so at our facility, we have a operations and maintenance contractor. It consists of about 6 mechanics, and part of their job is to every morning walk the facilities and do some general checks. So for us, it was as simple as adding a checklist item to their daily checklist. And that consists of 3 things when it involves Aqualogics. The first thing is they take a look at the monitor and they check for any alarms or any readings that are out of the ordinary. Then they inspect around the site looking for any leaks or anything that doesn't look right. And then they also check the actual tank, checking for the salt level. If the salt is low, they just refill it on site right then and there. We keep a pallet of salt in that room because we have a domestic water softening system as well. So it really wasn't that big of an issue for us to just order more salt and just keep it there on site. To give you an idea of how big the tank is, when we first filled it, it took about 24 bags to fill it up. And our mechanics during the peak heating season, they're filling it up every 3 weeks, approximately 8 bags. Next slide, please. Okay, so at our facility, we have a building automated control system that we have all the HVAC tied into along with our lighting. And we have a computer in our basement that our mechanics are frequently going on and throughout the day. So for us, it made sense to tie the Aqualogic into that unit. When we tied it into it, we used the BACnet integration, and that we were pulling points from it. We don't have any control functions, nor did we want any control functions. We can do that from the actual Aqualogic unit. We just wanted to have the alarms tied into the system to where if it goes into alarm, our mechanics would know right away. So we hired a third-party controls contractor to come out and work with Aqualogics to tie the unit in. I believe we were the guinea pigs and we're the first ones to really try doing this over BACnet. So we did run into a few issues. But Aqualogics, the team worked directly with our control guys, and after several visits, they're able to figure it out. And moving forward, I don't think this will be an issue because I think we, again, being the guinea pigs, we worked out all the bugs. And so I just want to add at this point, we do have a working system on our BAS, and we've tested it out. If it goes on an alarm, our mechanics are notified right away. Next slide, please. Okay, the maintenance. We had really 2 options. We could have Aqualogics, to sign a contract with Aqualogic to have them come out a couple times a year and perform the semi-annual maintenance, or we could train our mechanics on site. Because we have qualified mechanics there at our building, we thought it made more sense to just train them up to do this maintenance. So we hired Aqualogic to come out. They performed a full day of training. I sent 6 mechanics and then 2 GSA employees. And when they came back from the training, I asked them, like, how is it? Is this possible? And they're all very confident. They said it's very straightforward. Semi-annually, they go in and they just check for the filter, a couple of connectivity checks, about 15 minutes of quick inspection. And then annually, it gets a little bit more complicated where they have to actually calibrate the equipment and all that stuff. But they all came back very confident that they can perform this maintenance, and we have that worked into our PMI system. Next slide, please. All right, so this might sound like common sense, but I think what made this project successful, and in my mind, was just we had good communication from the top down. One of the things that we did from the very beginning is we brought one of the mechanics that's going to be working on this equipment every day into the meetings. We brought him, got his opinion. We had him up to speed on everything. at first, I was the liaison. We have a third-party chemical treatment company that takes care of all the chemical treatment for our cooling towers. At first, we were trying to relay information to him, but then we quickly figured out that it's much easier to bring him in as well. He speaks the same language as the Aqualogic guys, and once we got everyone into the room that's going to be on the equipment, things went very smoothly. As far as how we feel about the system, Aqualogics came to us and said that they have a piece of equipment that will save us water. And as a property manager, that's all I'm looking for, and that's what it's doing. It hasn't really made any change to our, like Greg said, it's not causing any more corrosion, any scaling. So it's not affecting our system, and it's reducing the water. We have a facility across the street that we're actually budgeting to install a similar system as this. So with that said, I'm going to turn it over to Jay.
Great, thanks, Jacob. So this technology that we're talking about today is part of a larger group of technologies that we call alternative water treatment, or since we're the government, we put an acronym on everything. It's AWT. So we've evaluated 5 different AWT technologies, and I want to tell you a little bit about show you some commonalities and some differences in them as we have gone through those evaluations. Next slide, please. All right, this is a kind of a busy slide, so let me just kind of orient you really quickly to what you're seeing here. So 5 different technology providers of alternative water treatment technologies across the top. Each column represents one of those technologies. And then down the left-hand side are different metrics or attributes that we looked at on those evaluations. And I don't want to go through every single one of these, but I want to point out a few key items for you. So if you look at like the fourth row down, it's water and sewer savings. And if you look across that line, you can see that every one of those technologies provided some savings. And actually, I would say every one of them provided significant amount of savings. The other thing I want to point out, and this has been mentioned a few times already, if you go 3 more rows down to chemical use. So different technologies use different approaches to achieving these savings. Some of them completely eliminate chemical usage, and some don't touch it at all. So I think you have to kind of, if you're interested in these technologies and you're thinking about putting them in, one of the things you have to consider is it easier to just put it in and keep it and everything in place? You like your chemical treater, or you think it's good to have somebody come out and look at your system? There's opportunities to do that. If it's your old boyfriend and you want to get rid of them and you don't want them on site anymore, then you can do 100% elimination of the chemicals. Next slide, please. Okay, this is a continuation of that same slide. So orienting yourself kind of the same way. So across the top are the same providers of those alternative water treatments. And then down the left-hand side, now we have a different set of metrics, and these are all related to the value of the technology or cost information. So as we talked about earlier, to kind of normalize the field, we use a GSA average water rate for these. And when you look at that GSA average water rate and you look at the metrics for each of these, I'll point you towards the second to the last row, which is simple payback. So simple payback on these systems, right? The cost versus the savings divided by the cost of the unit, you're going to get, all of them are under 3 years of payback. Fantastic, actually, for payback. And then for SIR, all of them also have some really fantastic numbers. So in general, all the technologies we've evaluated in this field have some promise, and all are showing that they have great value for GSA. Next slide, please. All right, so a couple things to think about in terms of deployment recommendations. If you have an open cooling tower system, any of those 5 technologies can be applied. They're not unique to any specific type of system, so you can apply them anywhere you like. They're also pretty straightforward. Most of them are just bolt on. You tie them into the water, you tie them into a drain, you put in a little electricity, and they operate. Most of the issue, I think, is mostly just finding the correct place to put them. So as you heard earlier, it's good to put some of them close to a drain because they provide blowdown. You want to have an electrical source, and you also want to be able to tie into the water source. We like these things so well, we're actually evaluating 2 additional AWT systems that are another twist on kind of how to do things. They're not exactly like any of the 5 we've done already, and they also look pretty promising. This seems like a really great field and a really great opportunity for moving forward into future water savings. Next slide, please. Okay, a couple things to think about in terms of deployment considerations. Water savings are site specific. So I think everybody can understand that if you have a longer cooling season and you're in a hot climate, you're going to get a better return and you're going to have more opportunity for these technologies. On the right-hand side here, you can see we have this kind of the equivalent, full load equivalents. So places like Pacific Northwest are maybe not be as much of an opportunity, although I think you could probably find that there are some places where it would make sense. And then a place like Hawaii is a place where, you know, where you're running full season cooling or full year cooling, there's going to be much more opportunity. This is probably the place where I should make the corny joke of, if you're going to go put one in Hawaii, then I would like to go install that for you. But because of Corona, I'm going to save that for some future opportunity. So you can look forward to that joke in the future. And the other thing is that the water quality dictates the cycles of concentration limits. So I think this is, if you're going to install one of these, I think one of the things you should take a look at is our website, the gsa.gov/GPG. Take a look at the different technologies that we've evaluated, and you can kind of get an idea of which ones might be best for your specific situation. All right, with that, let's go to the next slide, which I believe is a Q&A. Okay, I'm going to switch gears real quick so I can see questions. And those of you who are presenters, if you'd be ready to kind of unmute yourself and help me with these. So first question we have is, were there any energy savings due to better heat transfer? Did you M&V energy savings? So Greg touched on that a little bit, but Greg, you want to go ahead and cover that?
Yeah, we did not. Some of these evaluations, we do that. We measure energy usage from chillers and cooling tower fans and the whole bit. But on this technology, that wasn't a target. I think in retrospect, it might have been a good thing to do because I think there's a potential for that. So yeah, I think the fact that you keep scaling and everything in control, and it has the side stream filtration to get rid of biofilms, I think that's a potential, but we did not measure that, is the answer.
Okay, great, thanks. All right, the next question we have is $16.76 per kilogallon. That's what we identified as the GSA average cost for water. It says that's very high. Do you have a sense for certain price/rate at which point it makes sense? So you may say that that is high, and I think that depends partially on you know, what your unique situation is at your location. That is the average across all of GSA, what our water rates are. I don't know that we did actually, well, I don't know that we really need to actually take a look at where it makes sense. I guess, you know, that's the rate that we use. We didn't do any analysis on, you know, different rates where it would apply. Greg, do you have anything on that? Did we take a closer look at any of that?
No, I mean, there's several factors that go into the economics. I mean, if you can put a system in at a larger facility with a larger load, the economies of scale make it better. I think that if you look at the economics on the slide, the savings is all in the water savings. So if you wanted to apply a different water rate to those savings, you know, $10 or something like that, you can ratio down the water savings, and then that'll ratio the payback based on those costs that are listed. So you can go that direction, but there are several factors that go into the economics. And if you started at different cycles of concentration, you know, that could affect your savings. If you're a larger system, the economies of scale make sense, because if you double the size of the load, you don't double the cost of the equipment. So a lot of those go into it. But from the water standpoint, yeah, if your water costs are half of that, I think it's fairly simple just to kind of ratio those savings down.
Okay, great, thanks. I'm not sure where to go next here. Let's see. We have a couple of questions about people sent in applications to be part of GSA water treatment program. Not sure exactly what that question is related to, but we do have every year we put out a request for information, or RFI. That usually comes out in the fall, like right around early October. We just had one, it just closed. If you did submit to that process, those selections are done sometime in spring. The final selections are done around in springtime. That's how this technology was selected, through one of those RFIs, and that's how we feed our pipeline of future projects. Any other questions we need to address here? I'm not seeing anything else on this Q&A sheet. Anybody else have questions? This would be a great time to pop them into our Q&A down there at the bottom of your screen. Okay, I'm apologize. I have to read as I'm going here. It says, can you talk a bit more on how water consumption is normalized for cooling load within the building? Assuming occupancy is the main driver, how was that measured? That's a good question. Greg, you want to tackle that?
Yeah, primarily the way you can do that, we measure the makeup water and we measure the blowdown water. The difference is the amount of water that's evaporated. And again, there was also some drift losses, and through various calculations, we estimated what the average drift loss was too. So we know the amount of water that's evaporated, and the evaporated water is a good indicator of what the load is. So we've done it in the past where we use more complicated curve fitting technologies where we look at humidity and ambient temperature and that kind of thing. But the basic principle is if you're evaporating X number of gallons of water, that's your heat load. So we looked at all of the evaporation load during the baseline testing. Then we looked at all the evaporation load during the test period, and we adjusted it based on the number of days of each and the amount of water evaporated, and then compared it. And again, the metric that you end up with is water savings per ton hour of load, which is basically evaporation.
Okay, great, thanks. Okay. We have a question about, how about this one? Did COVID-19 play an impact? Greg, you want to take that?
I don't know. It might be a better question for Jacob. I don't think it really did. The only impact it might have played is, as we were trying to, go back out and, retrieve instrumentation and that kind of thing. Travel was limited. Our meetings were limited somewhat by travel. But I think once the system was installed, there really wasn't a lot of need for Aqualogics to come out and troubleshoot the system or do anything to the system. The people on site were trained to do any calibration that's required. So yeah, I think COVID was minimal.
Anything you want to add, Jacob?
Yeah, I mean, I concur. I mean, this whole install and the whole evaluation period took place before COVID was even a thing. So no, that didn't have any impact to this whatsoever.
Great. And then we have a question about how frequently does the softener media need to be replaced, and what's the approximate cost? Jacob, do you have any insight into that?
I guess I'm not following the question. I mean, as far as like what we ran into so far, the salt, every 3 weeks or so, the guys are adding 8 bags of 40-pound bags of salt. As far as like any of the calibration or meters, those get inspected yearly, and I believe there is a filter that they estimate will be 3 to 4 years before we need to replace it. But the cost on all that is very minor. And like we mentioned before, our maintenance contractors are doing all the maintenance in-house.
Okay, great.
I think Todd might be asking on the resin too, and I don't have that answer, but we can sure get back to him.
Okay. There's a question about what are the other 2 technologies that are up for evaluation. I'll cover that quickly. One is a blowdown recovery system, which will capture blowdown, filter it, and then recycle it back into the system. And the other one is an inline system that has a proprietary technology in a pipe that changes the chemical makeup of the water so that instead of scale developing in your system, it becomes, changes that to a flushable compound that just goes down the drain. So scale doesn't accumulate in your system. Okay. Was the softener backwash water deducted from the cooling tower blowdown savings in your calculations? Was the amount of backwash water significant relative to the tower blowdown?
We measured, basically we drew a box around the system and measured all water incoming and all water outgoing. So that wasn't an issue, and I don't think that amount of water is substantial. But yeah, we measured everything coming in and everything going out of the cooling tower and the new technology.
Great, thanks. And then I have a follow-up to the question about the media and the softener tanks. So Todd has indicated that those do wear out over time and they need to be replaced. So Todd, we'll reach back to the manufacturer and find out about that and get a response, and then we'll put that in our Q&A document.
And Jay, I'm just going to jump in because we do have a response from the manufacturer in another window. So that the media needs to be replaced about every 12 years at a cost of about $2,000.
Great, thanks. Anything else? If a building's interested in exploring this technology for installation in their building, how do they do that? Well, that's a great question. So I would say as a starting point, I think you can look at our evaluation on gsa.gov/GPG. Tells you information about the vendor, the provider, and also what we did, and also give you some idea of how you could spec that out and then where it would apply to you. I would really encourage you, if you are looking at these systems, that you look at all the reports that we've put there so you can find the one that's the best fit for your building. I missed when we stated what the exact water technology that was tested was. Since salt was used, were we testing an electronic ionization system? Greg?
Yeah, it's the standard water softener. It uses a resin and ion exchange. It's just normal water softener. The difference is in how it's used, and it does partial water softening instead of full water softening, and monitors the system, to be precise in that effect.
Okay. I think we're running out of questions. Anybody have any others they want to pop into that Q&A at the bottom?
Greg, Greg and Jay, we have one more question about whether it can be reused. If it's, I'm not sure if it means reuse or use, but and applied to an aging tower.
Can the technology be applied to an aging tower?
I assume that's what their question means.
Yes, it can. And I don't know exactly what aging means. I mean, the tower wasn't new at this site either, but I think that was that the question about passivation.
Well, there is, Greg, that was another comment about that was in the chat, and I don't know if you want to talk about the aging and the impact of that.
Yeah, I'm not sure exactly what the question is. Yeah, I think again the system is not very intrusive. Again, it sits off to the side. It keeps the water quality, within a narrower range than you probably would otherwise. If you have any upset conditions, you get alarmed, so you really don't go out of bounds very often. So, or if ever. So, I think the answer is it can be used on a new tower or an existing tower. And again, it's not an intrusive system that's going to change a lot of chemical characteristics of the water.
Okay, great. It looks like we definitely are out of questions. So if there are any questions that we didn't answer, I know there was a question about which of the 5 systems offer online monitoring. We'll be getting back to you on that, as well as sending out kind of the top Q&A along with the webinar recording and slides. And as we mentioned, you should shortly be receiving a survey. By completing the survey, that's how you can get access to continuing education credits. So thank you again. Thanks to all of our panelists and to all of you attendees. And we will be hosting some more GPG webinars starting in January, and you'll be receiving those. We'll be sending those invites out shortly. So thanks again, and we'll see you on the next webinar.